from Peking University. It's my honor to introduce our recent work in OpenFOAM workshop. The topic of this talk is enhancing computational fluid dynamics simulation through GPU-accelerated sparse matrix solvers in OpenFOAM. And there is outlines. In combustion simulation, there has long been a trade-off between accuracy and efficiency. And currently, in engineering field, RANS and LES method have been widely applied. But however, these methods, which contains many physical assumptions, are increasingly unable to meet the requirement for detailed numerical simulation under extreme conditions. While DNS direct numerical simulation is a first principle method for combustion, but is still considered a computationally unaffordable simulation method. And currently, the field of combustion is using AI and GPU efforts, trying out advanced AI algorithms and high-performance computing powers to address the efficiency and accuracy trade-off. Firstly, AI algorithms are currently maturely applied in combustion chemistry and other simulation aspects. And on the other hand, safety platforms are actively being ported to high-performance many-core hardware for acceleration. Therefore, it can be seen that AI and HPC technologies are making the detailed, chemically accurate DNS affordable. And a lot of work has been done in AI and GPU-assisted combustion. However, the current research lacks support for the combination of AI and GPU methods, large-step implicit solving methods, and studies on related parallel algorithms. Therefore, this work wants to develop an integrated framework that supports both GPU acceleration and machine learning models. The detailed objective is that we will complete the fully porting of combustion simulation software to GPUs. And as shown in this figure, all the time advanced operation will be conducted on GPU. And the specific computational patterns include the implicit PDE, neural network inference, Newton's method, and high-order temperature polynomials. Then I will introduce the code baseline. DFlame is the first large-scale open-source platform that couples AI framework for simulating reacting flow. And this figure shows the main features of DFlame. It's constructed on OpenFOAM, Cantera, and LabTorch. And here is the GitHub link of DFlame. You can find more information here. But however, in terms of hardware support, DFlame currently only supports heterogeneous computing for the AI module. Next is I will introduce the detailed implementation for PDE solving. Mainly contain two parts: the matrix construction and linear system solving. In general understanding, the solving linear system is the most time-consuming task, and there are lots of third parties developed by HPC and the math community, such as AMJX, cuBLAS, cuSolver. And it should be noted that the AMJX wrapper also makes AMJX available in OpenFOAM. And followed this method, DFlame also utilized the AMJX to solve the PDEs. However, as shown in the right figures, we can see that the time spent on the matrix assemblies is comparable to, or even longer than, the time spent on the linear system solving. But there is currently no solution for accelerating sparse matrix assembly, despite their often dominant role. So we decided to work on this topic. And then I will briefly introduce the matrix assembly process in OpenFOAM. The matrix assembly process mainly build the coefficients matrix A and the source term vector B. And here is the relationship between mesh and matrix. the matrix A is n multiply n, and the n is the number of mesh cell, and so is the dimension x and b. And we should know that cells are connected to each other through internal faces. Each face has an owner cell and a neighbor cell. Then we take a look to the matrix. We can see that most coefficients in A are 0. This format of matrix is LDU with lower, upper, and the diag are stored separately. Then is we'll introduce the PDE solving part. First is constructing LDU matrix, and here is an example of discretization of the Laplacian term, and as shown in this line, the upper and the lower interests are directly obtained by through the multiplication of phase values. That's why I use LDU format to construct the matrix is quite convenient. And then we need to then the matrix format need to be converted from LDU to CSR or LDU to ELL because the LDU format is not suitable for linear solving procedures such as SPMV, sparse matrix multiply vector, one of the most important operation. And then we can use AMJAX to solve the linear system. The input is AXB and the output is nu x. And recently we implemented an independent linear solver, which is named the DF linear solver, and we mirrored the OpenForms implementation of BICG step and PCG in GPUs. And then I will briefly introduce the preconditioner in DF linear solver, GAMG, geometric algebraic multigrid. And compared to the AMJX, we implemented the geometric multigrid, and it can improve the performance. And in detail, the GAMG integrates geometric and algebraic information to construct the efficient multi-level grids and the preconditioner. Next is the conducted optimization. First is the DNN innovation. We adjust the inference batch size and we reduce memory footprint while ensuring fast inference speed. And here we can see when the batch size is set about 8,000, the inference procedure features acceptable performance and keeping a quite low memory footprint. And for the CUDA kernel optimization, the first way for the memory bounded function, we adopt a data co-list approach to enhance data locality and reduce memory access overhead. And for the compute bound functions, we optimize by using memory instead of computation, splitting kernels and utilizing constant or the shared memory. And here we can see all the kernels shows good performance and then limit the hardware and near the hardware limit. And here is the parallel approach. We use NCCL for direct GPU to GPU communication. And here is the progress we have made so far. Like the implemented schemes, DDT, DIV, Laplacian, and the implemented boundary conditions, and the implemented solvers includes the AMJX, BICG step, and the JMG PCG with the CSR and the ELL matrix format. Then is the result. First is the reactive Telegreen vertex. It is a recently built combustion benchmark. And from these figures, we can see that the simulation result from the GPU DNN is same with the result from the GPU CVOD and the other results from the state-of-the-art codes. And in this figure, we can see that the 4 V100 GPUs achieve a nearly 35 acceleration compared to a 32-core CPU. And in these figures, we can see the implicit discretization part, we get nearly 75 acceleration, and in the solving part, which is conducted by AMJX, we get 4.3 acceleration. By further using the JM GPCG to solve the P equation, we got an additional 5 acceleration. And here is the memory footprint. We can see the memory usage for 4 million grids is controlled with 10 GB. And additionally, with the use of the CUDA stream allocator, the memory footprint of safety data get reduced of 2.27 times. And there are other results. The Cambridge burner, the laboratory scale turbulence cases can still achieve high simulation accuracy. And in this project, we implemented a full process GPU fully implicit simulation solver. And with the tests demonstrating that the AI plus GPU method can achieve acceleration by 2 orders of magnitude. And the implementation of common boundary conditions and the numerical schemes was also completed. And we replaced and optimized the AMJX to further enhance overall computational performance. And for the future, we plan to conduct large-scale scalability tests and conduct a test across multiple platform architecture. And we will package for OpenFOAM and the DeepFlame community to reduce usage complexity. And that's all. Thanks.